Morning session. Henriques is going to tell us about higher twisted K-theory a la Dadarlat and Pennig.
Well, thank you very much. So the first thing that I want to emphasize is that this is an assigned talk. So it was not me who chose the topic of this talk. It was the conference organizers, well, more specifically Konstantin Telemann, who asked me if I was willing to give a talk on that topic, and I said yes. And I would like to say that this is an idea that I like very much. And I have enjoyed preparing this. This is not my material, but it was great for me to learn about it. I think this is a good format to have. And if you ever are in the position of, in the future, organizing conferences, I encourage you all to include a little bit of that, because I think this is a great format for scientific interaction. Great. That being said, this is a talk about twisted K-theory, so which is via Caesar algebras. So let me first start by some generalities about Caesar algebra K-theory. This is going to be all very basic, but I think it's worthwhile to just put it down there. Two projections in a Caesar algebra are called equivalent, Murray von Neumann equivalent, if there exists a unitary in that Caesar algebra such that P is U star and Q is U star U. Partial isometry, yes, indeed. An element of the Caesar, thank you, Sarah. If U is unitary, this is always 1, and that's always 1, and that's indeed a true statement that 1 is equivalent to 1, but that's not what I wanted to say. Great. So now, if A is a unital Caesar algebra, then one defines K0 of A, the 0th K-theory group, to be, so you take the set of equivalence classes of projections under the above equivalence relation, except I don't want them to be projections in A. To take I want this to be a projection in the stabilization of A. A tensor compact operators. That's a set. It's actually a semi-group under the operation of direct sum of projections. And you take the group completion of that semi-group. So GR stands both for group completion, so force this into making a group, and also for Grothendieck, because he's the one who used that to great results to make, well, in his definition of algebraic K-theory. So here I wrote A tensor compact operators. I could also, if I wanted, write a co-limit as n goes to infinity of A tensor n by n matrix algebras. It doesn't really matter if I use compact operators or if I use this co-limit when I get the set of projections. You will get homotopy equivalent, you will get isomorphic spaces, isomorphic sets. And this can finally also be described as finitely generated projective A modules up to isomorphism, and again, group completion of that semigroup.
What do you say co-limit rather than
co-limit means that I have a system of things that becomes bigger and that include into each other. A limit is a thing like when you construct the p-adic numbers, where you have a system of things that map via projections.
Inverse limit.
Okay.
Great. So that's K0. Then there's also K1. So let me tell you about K1. Again, I'm assuming that A is a unital Caesar algebra in order to write down the definition. That is, by definition, the group of connected components of, and then I'm going to again use this co-limit thing. Co-limit as n goes to infinity, and now I put the unitary group of this amplification of A. So take the unitary group, pi naught. If I write pi naught of co-limit or co-limit of pi naught, it doesn't matter. Really, this is a misnomer. This really should be k minus 1. If I was doing real K theory, this would be k minus 1, except that in complex K theory, there's Bott periodicity that tells you that Kn and Kn plus 2 are the same. So this is a complete definition of K theory groups. So one can do K theory at various levels. One can do K theory, one can talk about the K theory groups, and I defined them. One can talk about the K theory spaces, and one can talk about the K theory spectra. They contain each one more information than the previous one. You can recover the K theory groups as the homotopy groups of the K theory spaces, and you can recover the K theory space as, well, there's a functor from spectra to spaces, and you apply that, and you go from the K theory spectrum to the K theory space. Let me tell you a little bit about that, because that's going to be relevant. So the K theory space, which I'm going to denote this type of K of A, well, the quickest way to define it is to say that it's the space that represents the functor which to a random space X assigns K0 of the C-star algebra of continuous functions on X with values in A. Yes, X is compact. X is compact, and so there's a little bit of fudge here in order to actually explain what this represents, because this space will not be compact. So I'm taking a non-compact space, and I'm only testing it using compact spaces. What this really says is that the space of homotopy classes of maps from X into that space, again, X is compact, is the same thing as K naught of compact continuous functions from X into A. And this should be true naturally in X, and there's at most one space that can be put here to make this equation true, and that space happens to exist, and that's called the K theory space. Now, there's also the K theory spectrum, which I will denote K underline of A. So a spectrum, the easiest way to talk about spectra is to say that a spectrum is, by definition, a sequence of spaces indexed by the integers along with comparison maps between each space and the loop space of the previous one. Each space and the loop space of the next one. Well, really what you do is the nth space of this spectrum represents the same thing, except you put Kn here. And at least, and there's very concrete ways of actually describing these spaces. This is a very abstract way. I can also tell you very concretely what these spaces are. So let me do that. The easiest one is for the thing representing K1 here. Well, that space is exactly the space that I use here. Like, remove the pi naught and just take that. That is the first space of the K theory spectrum, that colimit, period. For K naught, my talk is going to no longer be recorded as well as it used to be. Force. Well, presumably that's okay. For K naught, it's a little bit more complicated because of this group completion business. So this space here can also be described as So first I'm going to take the set of projections in A tensor compact operators. So projections inside a tensor compact operators, that's a space, and or I could take that co-limit if I wanted, that doesn't matter. And then I want to do a space level group completion, and that's denoted omega b, and that's a space level group completion. And in this particular case, so B is the classifying space, omega is loop space, but in this particular case, this can also be described as an infinite telescope with respect to the map from this space to itself that sends a projection to one direct sum the projection. So you take a projection in here and then do 1 in A times that projection, where you also use a shift in the coordinates of K to map that thing back to itself, and then that's a self map, and then write down an infinite telescope, and that's another model for that. Great. So that's the K-theory space, or that's the one model of the K-theory space. So let me start by a little lemma, which is that if I fix a projection inside that algebra A tensor compact operators, well, that identifies a connected component of really the space I care about is the space of projections inside A. So that identifies a connected component of this space, and that connected component is a classifying space for the unitary group of which algebra? Well, the algebra that you obtain by taking that and cutting it down by P. And I think that that's a kind of result that I can squeeze the proof of down in that last line. So let me write down that connected component by PR and then sub brackets P of this thing here. So what is that? That's just a projection inside an infinite dimensional free A module. It's a finite rank projection in there. And so that's the same thing as That's the same thing. That's the same thing as taking the image of that A module and look at all possible embeddings. So I look at embeddings of A modules from that given A module, which is P A tensor K, into A tensor K itself. And then now I have an A module plus a parameterization of it. I don't want that, so you mod out by the set of possible parameterizations, which is automorphisms inside A modules of P A tensor K. Well, and let's take them to be unitary automorphisms, then that group is exactly this, and this group is contractible. This thing is contractible because that's the space of all possible embeddings of something into something very infinite dimensional. Lots of room in there to make. So this is a contractible thing divided by the group that we want, and that's exactly the classifying space. So great, that's just a little lemma that I wanted to have down there. So the work of Dadarlat and Pennig focuses on certain very special kinds of C-star algebras, which come from bundles of Cuntz algebras, more specifically bundles of stabilized Cuntz algebras. So let me tell you first about Cuntz algebras. So I want to tell you about the algebra O infinity. So the first thing you do is you start by a regular planar rooted tree of infinite valence. So this is just the picture I drew. Like everything has infinitely many things coming out of it, and I pre-drew it. The Hilbert space on which I'm going to define my C-star algebra is going to be little L2 of the set of vertices of T. That's an infinite set. I take little F2 all of it. And there exist some operations I can do to this tree. Here's the thing to notice is that this subtree is isomorphic to the whole thing. This is isomorphic to the whole thing. And so there exists an isometry that I can write down which maps this whole tree onto the subtree. And that's not surjective, but that's injective. And I'm going to call that S1. And I could have done that with the second one. And I call that map S2, and so on. So this algebra, this Cuntz algebra, is generated by S1, S2. It has infinitely many generators acting on that Hilbert space in this particular way, and you generate a C-star algebra. So you put those things, they're adjoints, which are going to be maps that take this and put it all the way to there and like send that to 0. And so you get this thing. There's, of course, also a variant when instead of taking an infinitary tree, I take an n-ary tree for some finite n, and that defines the Cuntz algebra On, except not quite. For On, you need to do a small modification because you will get a copy of the compact operators inside there. So a bit more complicated for finite n. For infinite n, this is a correct statement. So you can think about a general element of this Cuntz algebra as being as follows. You single out a subtree, say here, isomorphic to the whole thing, and another subtree, let's say this one here, and then an element that a partial isometry that sends this to that and the rest to 0 is a typical element. And actually, if I were to look at the star algebra generated by this thing, algebraically, that would be a basis. These things here would be a basis of this star algebra. So that's a pretty good understanding of what this thing looks like. Now, there's a theorem by Cuntz which holds for O infinity, also holds for On, that says that for any element of O infinity, assuming it's not 0, there exists A and B in O infinity such that AXB equals 1. And that theorem is obviously true for those particular elements that I drew here in blue. That's easy to see for those, but for linear combinations of those, it's less obvious. And this has striking consequences. One of them is that this algebra is simple. I mean, indeed, if I look at the ideal generated by X, it contains 1, so it was the whole thing. And here's another thing which is very useful to have and which follows from that easily. So here's a lemma. Suppose I have two projections P and Q inside O infinity, and I'm going to assume that P is not 0. Then there exists an equivalent projection, Q tilde, equivalent with respect to that relation, such that Q tilde is smaller than P. And the proof is extremely easy, so let me do it. So first of all, note that if I had taken some other element here, 1, as opposed to 1, I could also very easily find A and B such that that thing is equal to that chosen element. Just like take that element and multiply, say, on the left or on the right of A or B to get that. So write Q as A, P, B. And that's something you can do because of that theorem. And then let's look at what happens on this Hilbert space. So I have the image, the subspace QH, and QH maps to PB QH, that's now another Hilbert space, via the operator PB. And by definition of what PBQH means, this is surjective, right? This is defined to be the image of that. And now, by the operator A, I map back to QH, because this composite is equal to Q. And Q is just another name for the identity on QH. So this composite is the identity. Great. This map is surjective. I just told you why. It's also injective because it composes something else is injective.
Do you have to take the closure?
No, I don't. If I have a map to something such that if I compose it to something else, it's injective, the map was injective.
No, I mean the second.
Sorry?
Was the surjective?
Well, I'm defining this to...
I mean, you want the Hilbert space.
You don't have to take the closure. You can define this to be a non-closed thing, and then the map is an isomorphism, and then you can do an argument to show that it actually was closed. Otherwise, it wouldn't be possible to find an inverse that maps it back to the thing. Anyways, this is a subspace, and that's another subspace, and that subspace, look at it, it has a little p in front of it. And so it is a projection onto that subspace, called that Q tilde, satisfies exactly that property. And this operator here, well, maybe not that one, but its polar decomposition will be the thing that you use here for this U here. So, what's a corollary of that lemma? Well, it's not exactly a corollary. It's a corollary with some work. So corollary, but you need to do a little bit of work, which is that the set of projections inside O infinity is already a group. So if you look at what we have here, first of all, we didn't take projections in A, we took projections in something a bit bigger than A, and that's because we were not able to add two things in A. Maybe I take something and something else, and it just becomes something that is outside of where I can put it back in A. Now this is okay, because if you look at a projection, suppose my projection lives somewhere here, it's going to be equivalent to a projection where I sort of like and put it back to live only here. And I take another one, and I put it there, and then I can take the sum of this and that. So some exist. And this tells me that differences also exist. Because if I want to take P minus Q, I replace Q by Q tilde, and now look, Q tilde is inside P, and I can take P minus Q tilde, and that's an actual projection. So we have sums and we have differences, and so it's already a group. And you need to remove 0 because 0 is just a bit different, and we had this assumption p not 0 here, and we had this assumption not 0 there. That's why you need to remove the 0. And so you don't need to group complete it.
In particular, you also have projections that represent 0 but are non-zero.
Sorry?
In particular, you have projections that are non-zero but represent 0.
You have a projection that represents the element 0, which is not 0. The projection onto that part of the tree represents 0. Indeed, it's this minus that, and those two are equivalent projections. So I take something minus something equivalent, and therefore that represents 0. And so we get that this is on the nose the K0 group. Now, Cuntz also computed these K-theory groups, and he found that K0 of O, well, I'll do it for all the ONs. K0 of ONs is Z modulo n minus 1. K0 of O infinity is Z, and K1 is always 0. So that's a computation by Cuntz. And it's kind of easy to see from that picture that at least you expect that relation if you take an n-ary tree, because I have the projection that represents 1, which is equal to this plus that plus that plus that, which is n things that you're adding. So 1 equals n. And that's that relation. In O infinity, you don't have the relation, so. So this corollary, which says that essentially you don't need to take O infinity tensor K, you just need to take O infinity and everything goes well, has an analog at the space level, at the level of K-theory spaces. So in order to tell you about that analog, I need to tell you a little bit about the C-star algebra O infinity tensor K. So just like O infinity is defined on this tree, O infinity tensor K is going to be defined on an infinite forest, like disjoint union of infinitely many trees. So now you take this thing here, infinitely many copies of that same tree, and you take the C-star algebra generated by, well, those things like that in blue. Like whenever I have a subtree somewhere and a subtree somewhere else, I'm allowed to look at the partial isometry that sends one to the other and generate a C-star algebra, and that is O infinity tensor K. So the thing that you notice is that there is a copy of O infinity tensor K inside O infinity. If I look at this big picture up there, that is the same thing as what I see here. Just remove the root, and I see exactly the same picture. So there's a map from that big thing back into O infinity. There's some kind of self-similarity, some kind of fractal feature of that C-star algebra that makes all this story work. And so in particular, what we get is this K-theory space that was used to, this space that represents K1. So here, let me write it here. This co-limit of unitary group of now O infinity tensor n by n matrices maps into the unitary group of O infinity, which itself maps into that same co-limit of unitary group of O infinity tensor matrices. And similarly, if I take the co-limit of the space of projections on O infinity tensor n by n matrices, that maps to the set of projections on O infinity, which maps back into that co-limit on the set of projections of O infinity tensor n by n matrices. And when we're doing this, it's important to remove the element 0. And here it's important to remove the element 0 and the element 1. And here we remove the element 0. So those two maps well, let's look at the first row. If I have a unitary which is somewhere here, like it's like supported in some finite set of those trees, and I want to bring it back into O infinity, what you do is you take it and you smash it in here. And I want to say that this is actually something that is this composite is a homotopy equivalence. If I have a unitary somewhere, I can rotate it. So first you need some more space in order to like take some more of these and like rotate it so that it's like here, and then rotate it back so that it lands in there. And so these two things are exhibit. These are all homotopy equivalences. And so what you learn from that is that this thing here has the right homotopy type, is the homotopy type of the first space of the K-theory spectrum. And then you also learn that this is the same thing as that, and that isn't exactly what we wanted because we wanted this group completion thing. But let's not worry too much about that, because let's have a look at this lemma here that tells us about the components. The components are governed by unitary groups of amplifications of the algebra. But those algebras are themselves algebras to which this first argument applies, and so the homotopy types of the connected components of this are actually already good. And so that is homotopy equivalent to the first space of the K-theory spectrum of O infinity, and that is homotopy equivalent to the 0th space of the K-theory spectrum of O. So they have, you don't need to do all these funny things. You don't need to put this extra K, you don't need to put this extra group completion, you just get the right, sorry, I should have pointed up there. You don't need to put this extra K, you don't need to put this extra group completion, you get the right thing on the nose. Great. So, back to the work of Ulrich Pennig and Marius Dadarlat. Where am I? The theorem Dadarlat and Pennig is that for any space X, bundles over X with fibers stabilized Cuntz algebras mapping to K-theory twists over X is an isomorphism. So I should maybe tell you a little bit about K-theory twists, because I didn't tell you anything about them so far. And also because the K-theory twists that appeared in Thomas Schick's talk are not the same as the ones I mean here. They are a subset of those. Like the kind of twist that he was talking about map to these kinds of twists, but they're not all of them. And really, the value of this theorem is to produce a geometric model, operator theoretic model, for all the twists. And so, yeah, so if you think about what K-theory is, the K-theory, let's say, K0 of a space, K0 of a space X is the same thing as homotopy classes of maps from X into the when I just write K without anything else, I just mean K theory of the complex numbers. The K theory space of the complex numbers. That space is also known as BU cross Z. So that is K naught of X. And if now, instead of having one spectrum in which we're mapping, we had a bundle of spectra over X, and we were talking about sections of the bundle, then that would be twisted K theory. So let me repeat. If I take a trivial bundle, so the bundle that has BU cross Z as fibers and the base space is X. If I take the trivial bundle and I look at sections of the bundle, that's the same thing as looking at maps from X into my fiber. So sections of a trivial bundle is this. Sections of a non-trivial bundle is a twisted version of that. That's called twisted K theory. And so twists of K theory are the same thing by definition as bundles of spectra over X with fiber, the K theory spectrum of the complex numbers. So now, this isn't quite right. This wants to be right, but this isn't right. The reason why this is not right is that if I do it this way, I get too many twists. You want twisted K theory to be a module over untwisted K theory. And so this is a bit too general. The reason it's too general is that this will not be a module over, this will not ensure that property. And to make it correct, you need to talk about bundles of K-module spectra. So for any C-star algebra A, so this is a spectrum. It's a ring spectrum. It makes sense to talk about modules over that. This is an example of a module. Every C-star algebra produces a K-module spectrum. And now we don't want bundles of spectra, we want bundles of K-module spectra. And now that I added this, that's exactly what I wanted. Okay. So this is really the definition. This is by definition that. So let me now rephrase this result in a setup that is going to make it a bit less daunting, because bundles of K-module spectra, maybe you've never thought about spectra in particular module spectra, in particular bundles thereof. So let me rephrase this result. So if I take a bundle with fibers this, and I apply this operation, fiber-wise, I get a bundle with fibers K theory of that. So the first thing to say is that the K theory spectrum of O infinity tensor the compact operators is just K itself as a K module spectrum. And that's really the same as the content of the computation of Cuntz. Once you have that, you have this. K module spectra, by the way, are up to isomorphism completely determined by their homotopy groups. So really the meat of the statement is in the second thing, which is that the automorphism group in the category of C-star algebras of this, well, that always has a map to the automorphism group in the category of K-module spectra of what? Well, of this thing using that equivalence, that this map is a homotopy equivalence. That's the statement. And by the way, this thing has a name that's called GL1 of the K-theory spectrum. So this works for any A infinity ring spectrum. You can define GL1 of that spectrum, and that's a space, and, well, now we're doing the K-theory spectrum. So, to prove that result,
So that's supposed to be equivalent to the.
yes, let me tell you what the relationship is between this formulation and that formulation. If I look at bundles of these things, well, there's any type of bundle has a structure group. And what is the structure group? The structure group is this group here. And bundles of these things, they have another structure group, and the structure group is this thing. And so we're saying that these two structure groups are the same up to homotopy. And so that will make bundles of one type of thing the same as bundles of the other type of thing. Again, up to homotopy. This is like isomorphism classes of bundles. I'm not claiming that this is a homeomorphism. This is clearly not. This is just a homotopy equivalence. So, this theorem, as stated, there's really two strategies for that have appeared in papers by Dadarlat and Pennig, and one of the strategies is to use, so strategy one, and that was done by Dadarlat on his own, was to use that O infinity is simple purely infinite and nuclear. Simple, you know what it is, and I told you about it in this theorem of Cuntz. Purely infinite means that, well, infinite means that like a projection is infinite if you can map it inside itself. Purely infinite means that, well, if I was working with von Neumann algebras, I'd say every non-zero projection has that property. With C-squared algebras, you need to say that every corner algebra contains an infinite projection, where a corner algebra is defined to be like the algebra when you multiply it on both sides by some positive element and take the closure. Anyway, such a thing, like lots and lots of subalgebras contain infinite projections. A nuclear is something which I'm afraid I don't have any time to tell you anything about it right now. And algebras, separable C-squared algebras that satisfy those properties are called Kirchberg algebras. And so really what he has a statement that holds for every Kirchberg algebra that says, well, this will no longer be true. This is not going to be true that for any Kirchberg algebra, if I put it here, I get this thing. Well, you get something else. Whatever you get, put it here, and then the statement is that this map is a homotopy equivalence.
Is it a surjection then?
Sorry?
Is it surjective, that map?
This map here? It doesn't exactly make sense to talk about a map being either surjective or injective because it's a map defined up to homotopy. So, or rather, it will depend on what model for spectra you take. There's multiple models. I can think about a spectrum as being a sequence of spaces equipped with things, but there's other models that one can use, and the exact homeomorphism type of this will depend on your model. And maybe the answer to your question will depend on your model, whether it's surjective or not. This is like the kind of things that you happen when you work in an infinity categorical setup. Things are never invertible on the nodes, they're invertible up to homotopy. So this is the monoid of self-homotopy equivalences of K as a K of X module. This is, so yeah. And if you force me to commit to a particular model and ask me, is it surjective with that model, I would say most likely not. I have no reason to expect that it is surjective.
You could take the left-hand side to be your model.
Well, I want to be able to make sense of that expression when I also put other things. You're right. That would trivialize the theorem.
Well, the theorem says that will then say that that's legitimate.
So there's another strategy. And that's the work of Dadarlat and Pennig, which uses some other set of properties of the algebra O infinity. Uses that there exists an isomorphism, I'm going to call it psi, from O infinity to O infinity tensor O infinity. And not only is there an isomorphism, but there exists a homotopy, a map from 0, 1 into the space of Caesar algebra homomorphisms from O infinity into O infinity tensor O infinity. And a map, I'm going to call it U, from 0, 1, now closed on one side, open on the other side, into the set of unitaries of O infinity tensor O infinity with the following properties. H of 0 is psi. H of 1 is the map that embeds this into the first summand, so that's identity tensor 1. And H of t equals add ut composed with psi for all t in 0, 1, 1 not included. Okay, well, what is that? It's some kind of statement that the algebra is isomorphic to two copies of itself. That's
an isomorphism, right?
I should have said that this is an isomorphism. So that's called self-absorbing. But there's some more properties that you want, and this collection of properties is called strongly self-absorbing. So this is a Kirchberg algebra that's called a strongly self-absorbing. And so if you take an arbitrary strongly self-absorbing Caesar algebra, again, you have some analog of those results. I should point out, so let me say it explicitly, again, this is not going to hold. It's going to be like whatever it is. And here, if I put this into that, and I look at the automorphisms of K of A as a K module, well, then you don't quite get them all. You only get the ones that also preserve the order structure on K naught, which might be a non-trivial thing. Anyways, but it's almost an isomorphism. Certainly on connected components, it's a homotopy equivalent. You just don't hit all connected components. Yes?
Can I make a comment about the part 2? I mean, this is not only a statement about just the homotopy groups. You also have to check that the group structure on the left-hand side agrees with multiplication or the group operation or monoid operation that you have on the right-hand side. I mean, this is the statement is a statement about bundles, so it's like taking the classifying space on both sides of that map too. So you don't get that from the homotopy group computations.
stated like that, I mean, this is visibly a map of groups because there's a map. And so if you compute that's an isomorphism of homotopy groups, you have computed that this is a homotopy equivalence. But there's extra structure, indeed, as you're saying. So in the context of strongly self-absorbing algebras, there is more structure than in the context of Kirchberg algebras. And that extra structure comes from the fact that now that we have this, K-theory becomes a ring. Because if I have two elements of K-theory with coefficients something like that, I can view it as a thing like that and then like bring it back. So there's more structure on this thing if your algebra is strongly self-absorbing than there is if your algebra is just a Kirchberg algebra. So let's see, what is it that I want to say right now? Let me think about how I want to structure the last 10 minutes. So maybe I want to tell you a little bit about these two classes of algebras. These two classes of algebras, Kirchberg and strongly self-absorbing, they're like that. They overlap. Obviously, O infinity is in both classes, but there's algebras which are one and not the other, and algebras which are the other and not the first one. So they're not included one inside the other. Both of them are, modulo some conjectures in C-star algebra world, UCT, universal coefficient theorem conjectures, modulo such conjectures, these classes of algebras are completely classified. We know exactly how many there are. So let me tell you, for the Kirchberg algebras, what it is in order to know the isomorphism class of a Kirchberg algebra. You need to know the K-theory groups, so K0, K1. The identity element represents an element in K0, so you need to know what that element is. And that's all. Any two countable groups, countable abelian groups, can be realized as K0 and K1 of a Kirchberg algebra. And if two such things for a given algebra and another algebra are the same, then the algebras are isomorphic. That's for this class of things. So K0, K1, and the class of the element 1, which is an element of K0, is a complete invariant, modulo UCT conjectures. For strongly self-absorbing algebras, again, there is conjecturally a full classification, and K1 turns out to always be trivial, and K0, well, if you look at that, you want an abelian group which is isomorphic to its tensor itself. How many abelian groups do you know that are isomorphic? So an abelian group, A, such that A is isomorphic to A tensor over Z with A. And moreover, the isomorphism is given by this map. The map that sends an element little x to x tensor 1 should be an isomorphism. If you think about it, these things are very rare. They're essentially subgroups of the rationals. So subgroups of the rationals is what K0 of one of these things can look like. And then there's one more piece of structure that you need to remember, which is K0 has an order. Two things can happen if I have a subgroup of the rationals. Say Z. I mean, Z is the one that we care about. There's Z with the usual order structure, and Z with the trivial order structure, where everything is bigger than everything else. And those correspond respectively to the Jiangsu algebra and to the Cuntz algebra O infinity. And yeah, so the conjecture is that these are in bijective correspondence with a subgroup of Q and an order structure.
You want them to be nuclear as well?
Nuclear is, I believe, a consequence of being strongly self-absorbing, but Ulrich can correct
yes.
me.
This?
Yes.
It's almost like 3-bit approximation.
By the way, I also checked that yes, if you just simply assume your strongly self-absorbing algebra satisfies the UCT itself, then yes, it is one on the list.
Ah, wonderful. This is something that yesterday afternoon I didn't know, and I asked Chris, and now he confirms that. So these classification results are theorems if you give yourself the UCT conjecture. Otherwise, they're conjectures themselves.
Yeah, but also for the purely infinite simple case, if you simply assume UCT, then you have classification.
Great.
For the particular algebra.
Question about this classification, the isomorphisms, are they also unique when given?
Well, you have a theorem about
You
isomorphisms.
talked about the general, okay.
Yes, they are given by that. So
The isomorphisms are unique up to asymptotic unitary equivalence, which is essentially what's at the bottom of that board over on the left.
I would like to tell you a little bit about a couple of ingredients that enter in the proof in this second approach. First of all, I would like to tell you that the statement that there exists such an isomorphism, O infinity is isomorphic to O infinity tensor O infinity, is vastly more difficult to prove than any of the other statements that I had on the board about O infinity. O infinity is simple, purely infinite, all these things. You can sort of do them in like 5 to 10 pages. This thing, as far as I understand, you need to read the whole book in order to understand what's going on. So yeah, so this is sort of uses like some more high-tech machinery.
That one is not quite so bad. It's when you go further, then
Or when I go further down the board.
yeah, when you try to actually start classifying things, that gets harder. But just to prove that isomorphism is easier, significantly easier than the full classification.
Anyways, I found it difficult. Yeah, so let me give you a couple of results that you encounter on the way towards proving our theorem. The first result that you encounter is that the automorphism group of, so now I'm going to work with a strongly self-absorbing. The automorphism of A, so A is unital and strongly self-absorbing. The automorphism is contractible. And the proof is very cute. So I think it's worth spending 1 out of the 3 remaining minutes to do the proof of that before going to tell you the rest of the argument. Consider the following bundle over the interval 0, 1. So the generic fiber is O infinity tensor O infinity. And it's going to be a sub-bundle of O infinity tensor O infinity times 0, 1. So first let me draw that whole bundle. So O infinity I'm going to represent by a little interval, and here I'm going to represent it by some other interval, and I just take the product O infinity tensor O infinity with that interval. So I have this thing here. So the fibers are O infinity, and the fibers here are O infinity. And then I want to make a restriction that at this endpoint here, I only have this copy of O infinity, and I have nothing. So it's sort of, it's left open there. And here I want to have the restriction that I have only this, and there I just remove. So O infinity sits as a subalgebra of O infinity tensor O infinity, and I only take that in there. So this does not look like a locally trivial bundle, but it is. These things ensure that this thing is locally trivial, and actually globally trivial. So now, if I have an automorphism of O infinity, I can produce the following automorphism of this bundle. Suppose my automorphism is called alpha. I put alpha here. And now I'm going to put alpha on each fiber, and here the identity on each fiber. And if you look at it, what is this? This is an automorphism of this bundle. I told you this bundle is trivial, but it doesn't look trivial, but it is trivial. So if I make it trivial, what I have is a way of continuously going from alpha to the identity. Moreover, that way was done in a way which is completely canonical. It depends continuously on alpha. So this is a contraction of that space, exhibiting that it's homotopy equivalent to a point. So the next thing, of course, is to be like, well, I didn't want the automorphism group of A. I wanted the automorphism group of the stabilized version of A tensor compact operators. And for that, there is a, if I look at, so I'm only going to talk about what happens on connected components, meaning I'm going to not tell you about the question of this map at the level of pi naught, which is a sort of different story. So let me just look at the connected component of that thing, which I'm going to call automorphism sub 1. So that's the connected component of the identity of this thing here. The thing to do is to map that to the space of projections, well, not all projections, a certain connected component of A tensor K. And I'm going to map an automorphism alpha to where alpha sends the projection 1 tensor E11. So 1 is the element 1 of this algebra. E11 is the matrix element inside here. It's a minimal projection. So let me call this thing E. So this is the connected component of E of that space. The connected component of that space that contains the element E. Okay, this is a certain map that certainly exists. And what is the kernel of that map? It's the stabilizer group inside this automorphism of the element E. And the argument goes as follows. By a variant of this lemma, you prove that this is contractible. Just the same kind of arguments. You prove that this is contractible, and therefore you deduce that this is a homotopy equivalence. And then if you remember the lemma that I had proven at the very beginning of this lecture, a component of this space of projections is equivalent to the classifying space of the unitary group of A. And then that thing, the unitary group of A, I told you was the same thing as this co-limit of unitary groups of matrix algebras over A, because A, well, here I'm doing an argument that only applies to O infinity, like only applies to those which are purely infinite. But okay, this group ends up having the correct homotopy type as far as K theory is concerned. And so we end up with this being the same thing as the K theory space of A, except the connected component corresponding to 1. So that's a sketch of the general argument. Now I maybe want to finish with a comment about what happens if I take the complex numbers instead of the Cuntz algebra. The complex numbers is also something that satisfies this. There is an isomorphism from C to C tensor C, and all those things are trivially true. So where is it that the proof breaks down? Everything goes through all until here. Everything goes through. And what happens is that for the complex numbers, U of the complex numbers, well, that's just U1, that's a circle group, doesn't have the correct homotopy type. So we have this result that, and I want to replace it, to put it here, that says that if A is purely infinite, and actually it also holds for a different reason for strongly self-absorbing or strongly self-absorbing, then the inclusion of the unitary group of A into the colimit over n of the unitary groups of A tensor matrix algebras is a homotopy equivalence. This result holds for O infinity and fails for the complex numbers. And that result makes this not have the correct homotopy type, makes this not have the correct homotopy type, makes this not have the correct homotopy type. Which homotopy type do you get? You get BU1. You get a KZ2. So KZ2 is not what you want something else, and that's where you can sort of see the difference between O infinity and the complex numbers. Sorry for going over time. Thank you for your attention.
Is there anything known for other types of Kirchberg algebras? For example, if instead of trees you have products of trees or buildings or...
The result is general. This result, if I take this and replace it by an arbitrary Kirchberg algebra, so let me do it. I put A, then I forget about that. That's sort of like no longer a true statement. Then I put here A, and I put this here A. A is unital Kirchberg algebra, then this is a true result. Now, I don't know about other results that you might want. I guess there's a classification result saying that if I have two distinct Kirchberg algebras, then I can look at hom from A tensor K into B tensor K in the category of C-star algebras. And yes, that's also something which you can ask, is it the same thing as hom in the category of K modules? And that is a result which is not in the paper of Marius Dadarlat, but which is a very easy consequence of what he actually does. So it's essentially, well, it's something that just by looking at the argument is like, oh yeah, of course, you just like put B's instead of all the A's that appear on the right, and then like the argument works. So yes, so what you get is that the functor, the K-theory functor, from, so this is the cleanest way of formulating the result that I like, that the functor from, let's say, stabilized Kirchberg algebras, stabilized, so non-unital Kirchberg algebras, so things of the form A tensor K, where A is a unital Kirchberg algebra, two K module spectra, the functor is take the K module spectrum of, that this is homotopically fully faithful, with essential image being those K module spectra whose homotopy groups are countable. So this is essentially an equivalence of categories up to homotopy.
You need to assume UCT for that.
Yes, Kirchberg algebras that satisfy the UCT proper, that satisfy UCT.
Otherwise, you'll get ones which aren't isomorphic, but where the spectra are or something.
Yes, and those are conjectured not to exist. So, correct. This is something one needs to assume in order to formulate the statement in that way. So if I want to formulate it unconditionally, I would say that satisfy UCT. And now it's an unconditional statement.
In the earlier statement about where you get automorphisms in k modules of k, that's also an infinity space. Is that something that you see from these isomorphisms?
Yeah. So this has been dealt in great detail in those papers. It's just because of time constraints I didn't have the time to talk about it. So indeed, if you look at this combined with the statement that the thing is isomorphic to its tensor itself, what you end up with is that any any strongly self-absorbing C-square algebra is an E-infinity object in the category of C-square algebras. I mean, you have a multiplication, which is the inverse of that, and any composite of multiplications in any order are homotopic, because the space in which the homotopies take place is contractible. So it's an infinity object in here, and therefore, by applying the K-theory functor, you get an E-infinity object there. So now, that's a very unstructured way of presenting the thing. What Dadarlat and Pennig do is they provide a model, a very structured model of this E-infinity ring spectrum. So they provide a symmetric ring spectrum from one of these strongly self-absorbing C-square algebras. They construct a symmetric ring spectrum. It's all extremely explicit. I won't give you the formulas because I'm over time. And then they prove an enhancement of this that takes here the spectrum GL1 using, so they sort of, everything that you might reasonably want to formulate is in that paper and has been proven. So like where this has been updated to a spectrum and this has been updated to a spectrum, and they show that you got an equivalence of spectra.
I see no further questions, so let's thank Andre again.